All right, thank you. So yeah, our senior design project is the design, optimization, and construction of the optical damping and leveling flexure systems for an electric propulsion thrust stand. I'm Nate Allwine. That's Jeremy. And far right is Logan. Our faculty advisor is Dr. Christine. So a problem statement. WMU organizations that work with low thrust devices currently have no methods of obtaining direct experimental thrust data. Some of these organizations are WMU, Aerospace Laboratory for Plasma Experiments, ALPE, Western Aerospace Launch Initiative, WALI, Space Weather Atmospheric Reconfigurable Multi-Scale Experiment CubeSat, or SwarmX. This experiment data is very crucial to confirming the validity of the analytical thrust models, indirect thrust measurement, and thruster performance for the efficiency testing. Our proposal is pretty simple, just redesign, optimize, and construct these four systems into a torsional thrust stand originally proposed by Anna Watts. These systems, as I said before, are the flexure, the optical, the leveling, and the damping systems. So our main constraints, this test stand has to go into the ALPE vacuum chamber. The size of that vacuum chamber is 31 by 40 by 24.5 inches. Additionally, it is a vacuum chamber, so everything that we're putting in the vacuum chamber has to survive the vacuum environment. We're hoping for measurement accuracy around 10 micronewtons. The devices in our lab we're projecting to have thrust range between 10 micronewtons to 1 millinewton, so very low thrust. We're also hoping that our device is compatible with various different electric thrusters. Within the ALPE space, there's a lot of different projects going on at the same time with different thrusters, so we want to be able to swap them out pretty quickly and just be able to use the same thrust stand. Additionally, one of the things that we haven't really looked into that much, but will be a factor, is the thermal management for our system. Some of the thrusters that could be used in the vacuum chamber will get pretty warm, such as hall thrusters. Additionally, an April deadline by SwarmX was pretty tight to get everything constructed.
So that's what a thrust stand is. These are the principles and the fundamental equations of how we actually use the thrust stand to calculate the thrust. There are a few main parameters that we need to look at when we're calculating thrust using torsional thrusting. That is the displacement, the moment arm, and the not only the linear displacement, but the angular displacement. So the linear arm is a design parameter. And for our testing, it was about 11.875 inches when we did our validation testing from the axis rotation, which is our flexure rod. This diagram is a top-down view of kind of that physical process. On top of that, there's a optical sensor, which is mounted along the arm, which is mounted at that location of displacement, and that measures the distance from the optical sensor to the arm. So that will give you our displacement once you subtract from the zero factor. The yellow arrow shows our direction of displacement, so it's going to be positive displacement away from the thruster, away from the optical sensor. And on the back side of the torsional arm, there is the damping system, which was attached on the copper plates. To actually calculate thrust, the fundamental equations that we use are the torque equals force times the length of the moment arm, and torque also equals the torsional spring rate or spring constant times the angular displacement. That is a known factor in our design, and then the displacement is measured, the arm is known, and the angle is calculated, and we set those two equations equal to each other to solve for the thrust, which in this case is going to be the quantity of the torsional spring rate times the angular displacement all over the length of the moment arm. So to get these quantities, like I said, one of the first things that we need is we need that known spring constant. To get that, we bought two different flexure pivots, which are very highly precision manufactured pieces of hardware with a known spring constant. We decided on two I-30 flexure pivots manufactured by C-Flex, which each have a known spring constant of 3.261 pound-inches per degree. Once that was known, we're able to implement those into our design at the axis rotation, which is our flexure rod. The other dimensions are shown on the screen above, but they were not necessarily inherently necessary for the actual thrust calculations. For the locations of these flexure pivots, they're located at the top and bottom of the flexure arm inside the housings. And so they're mounted at that connection point where one end is going to be inside the rotational arm, inside the axis rotation, and the other side is fixed. They're at the top and bottom, as you can see. And then on the picture on the right side of the screen, there's a top-down view of one of the houses of the actual I-30 flexure pivot inside the housing. The next thing that we need is we need to measure displacements. To do that, we decided to use an optical displacement sensor, which is manufactured by a company called ALPE. This displacement sensor needs to be incredibly precise and accurate with at least precision up to or exceeding in terms of minuteness 1 micron. And then also inside this system, there's a second part, which is the BV133 vacuum chamber feed through. This is rated for a high vacuum chamber, which is the chamber that the test will be conducted in. This was not used in our testing because our testing was done in atmosphere, but it will be used for interfacing with the vacuum chamber once vacuum testing is done in future works. So that's the diagrams there, how that works. This is a picture of the optical displacement sensor itself. It has an operating range of 6 millimeters, which is the distance from the tip of the sensor to the surface of the target. It also has a target diameter of 1.6 millimeters. So that is the diameter of which the signal is actually coming outside of the sensor. The sampling rate that we use for testing is 2.54 samples per second. There is a large range of sampling that we can use with the hardware, but it was recommended by the manufacturer that the lowest setting is used for low velocity displacements, in which case we're dealing with very low velocity displacement, so 2.54 samples is chosen. The steady state temperature that we found during our conductions of the testing was 28 degrees Celsius. This is an important parameter when you open up the VI to run the sensor and actually collect data. So that is known for this, and that was found out experimentally. You have to set that yourself after you let the sensor reach a steady state condition. This is manufactured by Philtech, and also manufactured by Philtech is the BV133 feed through. It is high vacuum rated, like I said, and it is used with single or double channel displacement sensors, and we use a type D sensor, which is their reflectance dependent type of sensor, which means that the displacement is measured by the percentage of reflectance after it hits the target. So it's applicable for our design.
Right, continuing on to the leveling system of the thrust stand. The main purpose of it is to just level the entire system so that the gravity vector is perpendicular to the thrust stand arm. This is just so gravity doesn't influence our thrust measurements at all. Premise is really simple. We're just balancing the stand on 3 main points with adjustable height adjustments. That way we can level the system in both the X and Y axis. Additionally, we'd like to have real-time monitoring of the levelness of the system. So the SM25 micrometers were chosen for our height adjustment. These have travel range of 25 millimeters with sensitivity of 1 micrometer. The micrometers also have graduations of 10 micrometers. One of the main factors when selecting this was the axial load capacity. The rest of the systems hadn't been completely flushed out with their design yet, so we didn't really know how heavy the entire system was going to be. So we went with one of the highest axial load capacities possible for a system like this, just in case it could handle everything. So, a simple mounting bracket was also manufactured in-house. Pretty much it uses the thread that is on the micrometers to just screw in the micrometers and just hold them in place. Additionally, B channels were designed and manufactured here at Western. These are pretty much just so the micrometers have a nice area to slide into and securely hold them for when we're transporting it in and out of the chamber. Here's an image of the completed micrometer assembly. As you can see, the micrometer is that vertical part there. It's getting held in by that mounting bracket there, and the B channel is holding it in place. These micrometers are located at both ends of the base of the thrust stand, while a leveling anchor screw is at that third point that's kind of set within the optical breadboard system, so it's a more secure location. Additionally, a leveling sensor will be used. This is for the real-time monitoring of the levelness of the entire system. This is the analog devices ADIS 16209. This has the function of being an inclinometer and also an accelerometer. However, in this case, the accelerometer part of it will not be used. The inclinometer accuracy is 0.1 degrees with a resolution of 0.025 degrees. This is supplied with voltage from 3 to 3.6 volts, and the communication interface is SPI. A little bit more on the SPI communication for this device. Some of the acronyms that I might use are SS, or slave select, S clock, serial clock, MOSI, master output, slave input, and MISU, master input, slave output. Pretty much we're using an Arduino Do in this case as our controller. This will send communication signals to our device, and the device will send back data. So this is pretty much just an oscilloscope string of what a SPI communication string looks like. The slave select will send a signal to select the device that you're using, and then the serial clock is continuously running as the clock for the system. It is like a time communication system. The master output will send the signal, and then master input will get the signal.
So the dampening system is integrated into the thrust stand for three particular reasons. The first to reduce noise, the second to be vibration, and the third to assist bringing the torsional arm to rest after it's been deflected by a thruster. Electromagnetic dampening systems are the only systems really explored for this project. They're contactless and assist in keeping the amount of variables that will be at play to a minimum. Based off of one of the research papers we looked into that was titled Recommended Thrust Measurement Practices for Torsional Thrust Stands, recommended a zeta value, which is a dampening ratio of between 0.4 and 0.8. This would be one of our starting points to design the damping system. Adjustability is one of the other highlights, or really the design goals. Because of the wide variety of thrusters that could be equipped to this stand, adjustability of the dampening system is the primary target, whether we need to make it stronger or weaker. So for the analysis, the natural place to start is the actual equations of motion for the system with a free-body diagram. As shown above is a torsional system. Using the Laplace transform and second-order underdamped system response techniques, we can, with no initial conditions, we can relate this equation, which is theta s over tau t of s, which is just an approximation of how the dampening response should perform. It boils down to three specific characteristics: the dampening constant, the moment of inertia of the system, and the spring constants, which we know from the selected Flexure pivots. The dampening ratio can be expanded on by these coefficients and can be solved for on the equations on the left. The two parts of an electromagnetic dampening system are: one is the magnetic field source, and the other is the conductive plate. The conductive plate serves as the source of the eddy currents once the magnetic field penetrates it. Copper is very expensive, and so we were lucky to find an online scrap retailer to find a 1/8-inch thick piece of copper for a fraction of what a new copper plate would cost. It can be mounted to the top or bottom of the thrust stand, depending on if you're going to use a linear stage to move the magnetic field, which we'll talk about later. So if you're using it in a manual configuration, it would be mounted to the bottom, and the L bracket with the magnet right there would be mounted underneath it to adjust the height, which would adjust the strength of the magnetic field. So eddy current dampening is the one we chose to go with. It made the most sense from a approximation standpoint, considering the rest of the stand wasn't complete. It gave us high levels of adjustability because we could adjust the magnetic field. Electromagnets were the first design choice we proceeded with. They gave us two methods. One, we could actually physically move the electromagnet further from the copper plate or closer to a stronger magnetic field. The second being increasing the amperage through the electromagnet would allow us to increase the field strength. As terms of actual velocities we expected, we didn't really have a decent range using online machinery estimations. Typical vibrations occur between 1 and 10 millimeters per second. This is the range we based the force calculations off of, using this equation right above my shoulder. It takes three properties of the conductive plate: the thickness, the surface area, and the conductive coefficient of the material, ours being copper. So eddy currents are generated when a conductive plate is moved through a magnetic field. The relative motion between the two will cause the magnetic field from the source to generate currents within the conductive plate. Those currents will generate their own magnetic fields and will oppose the original magnetic field that created the currents in the first place. This relative motion and generation of magnetic fields will generate a opposing force between the two, and is proportional to velocity and the square of the magnetic field source. Dampening constant we can approximate using the change in velocity and the force generated. We can approximate the force using the velocity and the strength of the magnetic field. Using this approximation, we come up with a wide variety of dampening constants based off of the velocities and magnetic field source strengths. And so this is essentially, once we have the torsional stand fully catted, we can create a moment of inertia from that. It's not including thrust or counterweights yet, so this is still on the lower end. It will be heavier eventually. But using the zeta values earlier, between 0.4 and 0.8, we can come up with a range of moment of inertias that we can damp within those zeta values. And solving for the moment of inertia itself, shown there. And then we have just a step response plot of the four zeta values, and this happened at 0.5 Tesla, which is the strength of the magnetic field the plate encountered. These step response plots are just an approximation that should help us predict the amount of dampening performance. When we're actually testing, if it's too weak or too strong, we can just change the distance of the magnetic field or the amperage of the electromagnet if we continue to use. The strength of the magnetic field can also be solved using the equations of motion shown here. And so from the zeta value and the damping constant, we can approximate the magnetic field. We expected a range of roughly 330 millitesla. That would be incorrect when we performed actual testing. A much stronger field. Our original plan was to use an electromagnet. This would allow us to have two axes of adjustability, the first being the physical distance between the field source and the copper plate, and the second being the strength of the field generated by it varying the current pumped through the electromagnet. Because it had to be in a vacuum chamber, material selection was important. Delrin, which was selected, melts about 170 degrees Celsius and was a logical choice to support the windings. An iron core was used in the middle, and PTFE triple insulated wire provided by Phoenix Wire was selected as the material for the windings. Modeling electromagnets turned out to be a much more difficult problem than we initially expected. This led us to build a test electromagnet to verify some of the models we actually built, and then we actually wrapped the final electromagnet shown there on the bottom left with the Delrin and PTFE wire. Throughout our research, heat was mentioned. However, it was not made as apparent as I would have expected. These ended up being giant heat sources, way beyond our expectations. We actually ended up abandoning electromagnets altogether. We could not keep the heat under control. A water cooling system would need to be implemented to remove the amount of heat that they were generated. Water cooling in a vacuum chamber can be done. However, we decided to reduce complexity and prevent destruction of sensitive components inside the vacuum chamber if there were any leaks, to not proceed with that route. So a permanent magnet system was, we pivoted to a permanent magnet system. The L bracket systems you supported is shown here, an L bracket with a clamping slot and then graduated pole increments, and then we had leftover Delrin to use as a holder for the magnet. these would be clamped together. Originally, we wanted to have these graduated increments so that if the linear stage wasn't used, you could precisely set the distance between the copper plate and the magnetic field source. This ended up being a much more difficult machining task than initially planned, and so we ended up just abandoning the graduated holes altogether. You would just have to set it and then measure the distance yourself. The magnet we ended up going with was a 9/16 by 3/8 cylindrical N52 neodymium magnet, and just about half a millimeter away from the source, you could get about 0.55 Tesla. The linear stage was brought into the picture when we lost one axis of adjustability moving from the electromagnet to a permanent magnet system. We can no longer control its strength. To vary the dampening strength, we would need to move the magnet further or closer to the copper plate. A linear stage was the logical way to do this. A Belmex MN10 stage was used with an advance ratio of 0.00025 inches per step. This translated to about 158 steps per millimeter, and we could really move it as close as far as we needed to within the mounting range. We'd have to mount it higher or lower depending on if we want more or less adjustability. And there are two proximity switches attached to the linear stage itself that would prevent it, when properly set up, would prevent it from contacting the torsional thrust arm. And this is just a snapshot of the VI used to control it.
So after we had all the components finalized, all the subsystems completed, we moved forward with validation testing. To do that, we set up a procedure, which what we did is we set the thrust stand in the chamber, but not with the chamber closed, so it's exposed to atmosphere. And we developed a configuration system where we just had a mount made out of 80-20 extrusion that would act as a point of deflection for a string. So we took a weight and attached it to a string and attached the other end to the torsional arm that was located at about 11.87 inches from the axis of rotation. And we set it on top to make sure there was no horizontal deflection that could give us any erroneous zeroing data. After we let it settle for an extended period of time, we recorded 20 seconds of data and set the average of displacement as our zero. Those numbers were within accuracy of about 0.1 micrometer. After that, we then moved the magnet forward, or not the magnet, the weight. We moved the weight forward over the deflection point so that it would pull the displacement of the arm forward away from the displacement sensor and give us a positive displacement. Once that was done, we waited for that to settle in the chamber, and we took a measurement of 60 seconds, which gave us about 150 to 160 data points to estimate our thrust. Once those displacement values were taken, it was put into MATLAB using just a simple MATLAB script that interpreted the data from a .csv file and calculated thrust using the equations that were outlined at the beginning of the presentation. This was repeated 5 times with 5 different weights. On this slide, you will see 2 different graphs of displacement data. The first one is the whole wavelength, the whole wave, and that is from the initial application of the weight until it begins to damp out. That red square you'll see is that settling point that we're kind of looking at when the arm comes to rest and a constant force is applied, and it's not just oscillating from impulse at the beginning of the test. So that right picture is a zoomed in version of that little red box. In actuality, that red box would be much further down the x-axis, but to just keep it inside this slide would kind of give you an idea of the type of wavelengths we're looking at. They're very minute compared to the beginning displacement waves that you looked at once the weight was applied. So we did this for 5 different weights, and to calculate the expected force, we just use simple force equals mass times gravity. So the expected forces for the 5 different files are outlined in that first or second column, I should say, and then the actual calculated force from the VI and the MATLAB using our testing procedures are the next column. And the final column, you'll see our actual percent error. You'll notice there's a large fluctuation at different levels of percent error, and we attribute a lot of this to atmospheric interference and a bunch of other factors that will go on in the next further slide. But you'll see as well that the actual thrust curve is similar to the displacement one because it is proportional to displacement. So in terms of the calibration of the errors, source of errors, most of it could be chalked up to the atmospheric interference because this is intended for vacuum testing, and then also thermal drift and a couple other factors or things that we were not anticipating to account for. These would have to be investigated further for more precise results. In terms of future works and improvements for this, one of the biggest things is that a stronger magnet or thicker copper plate could be implemented into the system to give a stronger dampening coefficient. The motorized leveling system would be great for in-time leveling that's more precise. And then vacuum testing and further validation testing would be required to give you more accurate data on top of the in-atmosphere data we already conducted. So in conclusion, we were successful in implementing these three systems together so that they actually work and create an operating thrust stand. We think that the error could be improved and some of the sources could be a little bit more, and that further testing is required for this to be more precise. But the documentation and the test procedures for that have already been made, so they would be just, in essence, act of just doing it and reducing that error. So there's a lot of people we'd like to acknowledge, not least of all, of course, is Dr. Lemmer for letting us work in her lab and being our faculty mentor. We'd also like to thank Mohammed Asif and Hannah Watts for letting us work with them and under them in the lab, and also extending upon Hannah's initial research for the design and development of a thrust stand. We'd also like to thank all these other groups here and people, including our dear friends and family. These are sources for our paper for a lot of the research that we've conducted.
How would you measure the temperature throughout the system, and how do you think that would be effective?
We were considering implementing thermocouples throughout the system. Additionally, you can see the thermal drift within your data and use some algorithms and try and take out that thermal drift. Additionally, more complex route would be to try and solve it on the front end with like water cooling the whole system.
In the damping section, you mentioned that it is ideal to have a damping coefficient between 0.4 and 0.8. Why is it ideal to have an under-damped system versus a
It provides a better resolution target for the data and just a closer tolerance at the overall result.
If you wanted to measure, you also mentioned in the beginning that your measurement range is 10 micronewtons to 100 millimeters. That's a pretty big range of thrust. Does the thrust stand at this moment measure that entire range, or is it only partial, and what would you have to change to measure that range?
So far we've only tested in the millinewton range, so it's pretty difficult to get masses small enough to actually induce a force of micronewtons. So we can try that in future testing, but it's very difficult with the tiny objects that you need to use. Other question for you?
Yeah. So the Delrin wires, that's what you use for the
PTFE wires,
okay.
And then it was around a Delrin.
Oh, okay. Did you consider using maybe like a thicker wire to reduce any kind of?
We did. That would have required us purchasing more wire. Our original estimations used a thinner gauge wire, which no doubt contributed to the heat issues. But even with a thicker wire, for the field strength we needed, it would be impractical without an active thermal management system.
Okay, we give a pause. Yeah.